Okay, so this is problem 9-4. We have an RC circuit here. We have capacitor 1 has 4 microfarads, capacitor 2 has 12 microfarads, and resistance has 100 ohms. Okay, so A asks for, what are the final charges on the positive plate of each of the capacitors 1 and 2 after equilibrium has been reached? Okay, we are given that initially we have V naught equals 50 volts. To find the final charge, we have to first calculate the total charge, because that's what the whole entire system will be. So Q total at initial is equal to C1 equation C1 V naught, because this is initially uncharged. So this equals 4 microfarads times 50 volts, which is 200 microcoulombs. Okay, so we need to find after equilibrium the charges on both of these. Okay, so well, if intuitively, you can see that C2 is equal to 3 times the capacitance of C1. Since the voltage across these will be the same, that means that Q2 over C2, sorry, this is wrong. So we have V equals Q2 over C2, V2, right? This is, so V2 and V1 are equal, Q1 over C1. So, if you set these equal to each other, you see that Q2 over C2 equals Q1 over C1. And because C2 equals to 3 times C1, we see that Q2 is also equal to 3 times Q1. Okay, so intuitively you can see that, which means that Q1 is equal to 50 microcoulombs and Q2 is equal to 150 microcoulombs. You can see the 3-to-1 ratio here. Mathematically, we can calculate it. So we have V1 equals V2. And we also have V total from initial equals V1. From here we have Q1 over C1 equals Q2 over C2. From here we have Q1 over the total capacitance, actually this is Q total, sorry, C1 plus C2 equals Q1 over C1. So you see that Q1 is equal to C1 over C1 plus C2 times Q total. This fraction right here is 4 over 4 plus 12, which is 4 over 16. So Q1 is 1/4 of the total, which is 200. So from math, we get Q1 equals 50 microcoulombs. And we know that Q1 plus Q2 is equal to Q total. So Q2 is equal to 150 microcoulombs. Okay, I'll erase this part for part B. Moving on. Okay, part B. It asks for determine the difference between the initial and final stored energy of the system. Okay, so that means we first have to find initial. So initial stored energy is equal to, well, first off, C2 was uncharged, right? So that means initial is only based on this capacitor. So that's 1/2 C1 V naught squared. This is an equation. So from the equation sheet, so we can plug it in. 1/2 times 4 microfarads times 50 volts squared. Use the calculator, you can get 5,000 microjoules. Now we have to calculate final. Final, both of them have energy. So using V equals Q over C, we can do for this one 1/2 Q1 squared over C1. I got this from this equation, but I substituted V equals Q over C to there. So plus 1/2 for both. Q2 squared over C2. This equals 1/2 times the charge that we got from part A, 50 squared over 4 plus 150 squared over 12. We know the units will be in microjoules. If you use a calculator, you get 1,250 microjoules. So that means change in energy, remember the negative sign, is equal to negative 3,750 microjoules. That's the change. So, part C. I'll erase this. Part C asks for, write but do not solve an equation that at any time after the switches are closed relates the charge on capacitor C1, its time derivative, and the parameters V0, R, C1, and C2. Okay, Kirchhoff loop rule applies here. So we can go from, let's say, clockwise. So that means V1, if we're going in the direction minus I times R. Since these will have the same charge, but if you're going this way, it's different. So minus V2 is equal to 0. V1 is equal to Q1 over C1. I is the change in instantaneous change in charge versus time. So I is actually negative dq dt. Negative because this is discharging. There is no battery to supply voltage, so it has to be discharging to that. And V2 is equal to Q2 over C2. But we have to make Q2 in terms of the other function. So we know that Q1 plus Q2 is equal to Q total, which is also equal to C1 V0. So Q2 is V0 C1 minus Q1. Just substitute that in. So plugging all these in, we get Q1 over C1 plus, because two negatives, plus dq dt times R minus, plug that in, V0 C1 minus Q1 over C2. This has to equal 0. Okay, so part D. Part D. Okay. So we are given that the current in the resistor is given as a function of time. I equals I naught e to the negative t over tau. We given I naught equals 0.5 amps and tau is equal to 3 times 10 to the negative 4th seconds, time constant. Okay, so D. Determine the rate of energy dissipation in the resistor, also known as power. So, where we need to find power, which is equal to IV, in terms of time. We are given I is this, right? But we don't have voltage. But we know that from Ohm's law, V equals IR. So we can plug that in, we get P equals I squared R. Plugging this in gives I naught squared e to the negative 2, because exponents multiply, over tau times R. That's power. And notice, it is in terms of time. We have t right there. So that's D. I can do E here. I have enough space. So how much energy is dissipated in the resistor from the instant the switch is closed? So basically from initial to final. From part B, we determined that the change in energy was equal to negative 3,750 microjoules. Well, the energy had to go somewhere, and it is dissipated from the resistor. So from part B, you can say that the energy dissipated is equal to energy lost. But it has to be positive. So, change in energy dissipated is 3,750 microjoules. But, using mathematics, we've got to use power. So, we know that power is the derivative of potential energy per time. So that means potential energy, the change, is equal to the integral of power with respect to time. This is correct. P we use from the previous equation. So we have that change in U is equal to I naught squared R, the integral of P. Well, we got that from there. We have e to the negative 2t over tau with respect to time. Okay, so integrating this, you get I naught squared R. These are constants that are pulled out. So this has to be negative tau over 2 if you integrate it. E to the negative t over tau from 0 to infinity. Oh, I forgot. This is from 0 to infinity when we're taking it with respect to time. So this becomes I naught squared R negative tau over 2, 0 minus 1. So the negatives cancel out essentially, so this can be positive and this is gone. So this equals 0.5 squared. Plug these values in, we have I naught equals 0.5 amps, and tau is equal to 3 times 10 to the negative fourth, so plug it in. We have resistance, which is 100 ohms, so 0.5 squared times 100 times 3 times 10 to the negative fourth seconds over 2, and this does indeed, using a calculator, equal 3,750 microjoules. And that is problem 9.